as we have discussed earlier, that in a nucleus, there are protons and there are neutrons. Protons and neutrons. A proton is positively charged and a neutron is neutral. Let us apply a simple way of thinking. Okay, for example, in my hand I have a model of a nuclei where it has 3 neutrons and 3 protons. Okay, this is a very simple way of thinking. So in this particular case, let us exclude the thinking of isotopes for a while, for simple way of thinking. Okay, suppose as we can't see an atom, okay, it is very small, 10 to the power minus 10. Okay, so but we can apply something known as our thinking. So when I think that there is this particular atom that has like 8 protons, then it should be like 8 neutrons. Okay, for example, in this particular case, I am applying some kind of thinking. I am thinking about a nucleus and I am thinking that it has 8 protons, then it should have 8 neutrons. This is the case of oxygen. So this is my expectation in the case of lighter nuclei, and I find that my thinking was very much correct. It has 8 protons and it has 8 neutrons, and it's like, yes. Okay, the reality in the case of lighter nuclei. This is the reality in the case of lighter nuclei, where the number of protons and the number of neutrons are very much less. So now let us use a little critical thinking. Okay, not so much, a little critical thinking. What if I think of the number of protons to be above 80 or above 90? What is it going to be in that particular case? Is it going to be like the number of neutrons is going to be the same, or is it going to be different? Again, when I apply this simple way of thinking to heavier nucleus, and in this particular case I am thinking that I have 92 protons in the nucleus, I should have 92 neutrons in the nucleus. This is my expectation in the case of heavier nuclei, just like in the case of lighter nuclei. But again, it's physics, things do change. Okay, my thinking was of 92 protons. In case of heavier nuclei, I should have 92 neutrons, but it is not. It is 146 neutrons, and this is the case of 238 uranium. Okay, what happens is that as the number of proton increases, the number of neutron increases exponentially. Okay, as we move to more and more heavier elements, the number of neutron starts increasing in an exponential way. Okay, so reality in the case of heavier nuclei, no. Okay, so this heavy nucleus, okay, that is uranium 235. Uranium 235 is an isotope of uranium 238. This nucleus, okay, the nucleus of the heavier nuclei have this property of radioactive decay. They have this property of losing weight in the form of radiation. 3 types of decay: alpha decay, beta decay, gamma decay. In the case of alpha decay, we have the parent nucleus. Okay, these 3 are the parent nucleus. A parent nucleus is the original nucleus, okay, before the process of decay. And we have the daughter nucleus. Okay, this is after the decay. After the decay has taken place from the parent nucleus, when it starts decaying, then we have the daughter nucleus plus a helium nucleus. A helium nucleus, what we call as the alpha decay. Okay, in the case of daughter nucleus, a daughter nucleus is the nucleus left after the decay. Okay, so in the case of alpha decay, we have a daughter nucleus and a helium nucleus. Okay, in the case of helium nucleus, we call it as alpha decay. Okay, in this particular case we have 2 protons and 2 neutrons. It is a helium ion, therefore we call it as alpha. Okay, not a helium atom. We call it a helium nucleus or alpha particle. So, and then we have the beta decay process. In the case of beta decay, okay, this is the reaction which we are going to analyze more and more in details. In beta decay, we have the parent nucleus, and after the decay, the parent nucleus, there is a change in the parent nucleus. Okay, there is one change or two changes, that is the change of a proton into a neutron or a neutron into a proton, releasing an electron from the nucleus. Okay, so in this process, the conversion of a particular element, okay, a conversion of one nucleon or two nucleons takes place, releasing an electron. Okay, that is a beta particle from the nucleus. We have a electron. Okay, we have a beta particle. It could be a plus beta or minus beta decay. Okay, so this is your beta decay process. And then we have the gamma decay. In the case of gamma decay, I have the parent nucleus. Okay, the parent nucleus, there are certain things known as excited state. Okay, it has been told to us many a times, don't be too much excited. Okay, don't be too much excited, or happy days are only for a few days. Yes, sadness remains, etc. Okay, somehow it is also true in the case of atomic physics, okay, nuclear physics, etc. Even in this particular case, when the nucleus is excited, okay, when it is excited to a certain level, then it decays, then it comes down to a de-excitation level. Okay, so when it de-excites, when it comes down to its original level, okay, when the party is over, then it releases some amount of energy, and that energy is released in the form of photon, a gamma particle. Okay, it is released in the form of photons when it de-excites. So this is your gamma decay process. So it is something like this. Before, it was really huge, really big, and this is after the decay process takes place. There are two types of beta decay. One, beta plus decay, and another one is the beta minus decay. Okay, in these two processes of beta decay, there is emission of particles, okay, plus there is conversion of a particle. In the case of beta plus decay, in this particular reaction I am taking carbon 14. Okay, carbon 14 is an isotope of carbon, okay, that has 6 protons, the atomic number of carbon, 6 protons and 8 neutrons. Okay, 6 plus 8 is 14. So this is my carbon 14 atom. Okay, when it decays, when the carbon 14 atom goes into beta decay, okay, then we have 7 protons. In this case, we had 6 protons, whereas after the beta decay process, we have 7 protons, okay, and 7 neutrons. That means something has gone wrong. Something has gone wrong in this particular process. That is, I am losing one neutron. Okay, one neutron is less when it goes to N14. N14 is nitrogen, having 7 protons and 7 neutrons. Okay, there is one shortage of neutron after the beta minus decay. Okay, we have the daughter nucleus is this one, that is the nitrogen atom, and then we have the emission of electron. Okay, we have the emission of electron, which is your minus beta decay particle. Okay, minus beta particle, and then we have this one more particle called antineutrino. Okay, antineutrino. the reason why we call it as anti, okay, there is something known as neutrino and antineutrino. Okay, you guys have heard this somewhere or maybe not, but every particle, okay, every particle in this entire universe has an antiparticle. Okay, a matter and antimatter. I guess you have heard this phrase before also. Every particle or every matter has its antimatter. Okay, so just like for example, if I have a positive charge, I'll have a negative charge. Okay, if there is me as not like anti and there is someone just like me who is anti. Okay, I am Siddharth and there is someone just like me who is anti-Siddharth. Okay, in the same way, in the world of particle physics, we have this concept of matter and antimatter. So, an antineutrino is an antimatter of a particle known as neutrino. Okay, so in the case of beta decay, a neutron, okay, let me take this picture in a more precise way now. A neutron is changing into a proton, giving us an electron plus an antineutrino. Okay, it gives us a proton, a neutron changes into a proton, an electron, okay, a beta minus particle, and the antineutrino. And then we come to this beta plus decay. In the case of beta plus decay, just like in the case of your beta minus decay, where a neutron was changing into a proton, in the case of beta plus decay, a proton changes into a neutron. In this particular case, I am taking carbon 10. Okay, a carbon 10 has 6 protons, atomic number of carbon is 6, okay, and 4 neutrons. When it decays, when it undergoes beta plus decay, then it changes into a boron. A boron has 5 protons, atomic number 5, and 5 neutrons. Okay, in this particular case, I am missing shortage of 1 proton. So, 1 proton has changed into a neutron, giving me a E plus. This is beta plus particle. Okay, this E plus is also known as positron. As I said, every matter has its antimatter. Okay, in the same way, an electron also has its antimatter, that is a positron. Everything is same. Everything is same except the charges. A positron is positive, an electron is negative. This positron is the antimatter of electron. Okay, and then plus a neutrino. In the previous case, in beta minus, we had an antineutrino. Okay, antineutrino. In this particular case, we have a neutrino. So this is your beta plus decay, and making it precise, a proton is changing into a neutron, giving us a positron plus a neutrino. So this is what beta decay does, and this is where your weak nuclear force, also known as weak interaction, comes into play. It is not very easy. It is not very much, it is of course complicated, but it is very much interesting, because it is because of this force, the weak nuclear force or the weak interaction, we are standing here. You are watching the video, I am giving the lectures. Okay, so this is your case with beta decay. It changes a particle into another particle. Okay, now we had discussed something regarding the strong nuclear force. Okay, we had looked of what particles is a neutron or a proton made up of, and we said it is made up of quarks. So let us look into that picture. Okay, let us elaborate this particular topic in order to understand what is actually going on at the fundamental level. Is it possible to break up a neutron, a proton? And we had said that yes, they are also made up of some particles known as quarks. Quarks are elementary particles, and there are 6 types of quarks: up, down, charm, strange, top and bottom. All these 6 quarks has some charges and have some masses. All these quarks in the table, okay, the top row, the up quark is positively charged, plus 2 by 3, okay, the upper one, and the lower one is minus 1 by 3, that is negatively charged. Out of the 6, we are going to concentrate only on up quark and down quark, because these are the quarks with which a proton and a neutron is made up of. Okay. In case of your proton, a proton is made up of 3 types of quarks: up quark and down quark. Okay, it is made up of combination of 3 quarks, 2 up quark and 1 down quark. In the case of a neutron, it is made up of 3, again combination of 2 down quarks and 1 up quarks. So as we look into the picture of beta decay, okay, as we look into the picture of beta decay through these quarks, what is actually happening is that there is the difference of only 1 quark in a proton and a neutron. In this case, it has only 1 down quark, and in this case, it has only 1 up quark. So there has to be something regarding the quarks, the changing of the quarks, okay, that is going to take place in beta decay process, that is going to change a proton into a neutron into a proton. In the case of beta plus, we know that a proton is going to change into a neutron. So a proton has 1 up, 1 down, and a neutron has 2 down quarks. Therefore, there has to be 1 up quark that has changed during the beta plus decay. Okay, 1 up quark is changing down to 1 down quark, making it 1 up, down, down. That is a neutron, giving an electron and a positron, sorry, that is the antimatter of the electron, and a neutrino. Okay, in a beta plus decay, we have a proton, okay, where 1 up quark is changing into a down quark, making it a neutron, plus the emission of a positron, the antimatter of an electron, and a neutrino. Okay. In the case of minus beta decay, we know a neutron is made up of 1 down, and 1 up, 2 downs and 1 up quark. And in this particular case, it has to be that 1 down quark that is changing into an up quark, making it a proton. Okay, and emitting a electron and an antineutrino, that is the antimatter of a neutrino. Okay, so this is your picture of beta decay process with respect to the quarks. What is actually happening at the most fundamental level? Okay, is it directly a proton changing into a neutron, or one particular quark changing into another quark? Okay, so as I said, in this particular case, charge, an up quark is positively charged, a down quark is negatively charged. That is 1/3, 2/3. Okay, in this case, I have 1 up quark changing into a down quark, a positively charged quark changing into a negatively charged quark. Now, has the charge been violated? Okay, in the case of beta decay, then quarks are conserved. There is something known as lepton numbers. Okay, an electron is a lepton. Okay, it is conserved. The charge is also conserved, and the quarks is also conserved. Okay, but how is it possible that a positively charged quark is changing into a negatively charged quark? Okay, in this particular picture there is one more particle that is playing this magic, that is doing this magic entirely. Okay, and we are going to reveal that magic. Till now it seems like a magic because one particle is changing into another particle. That is what I said regarding your fundamental forces, that the reason is magic if you do not know the force, and the reason is physics if you know the force. Okay, till here it is magic. The moment we are going to know which is that particle, which is the particle that is changing, one type of particle into another type of particle. Okay, and this is why I told you in the beginning that this particular topic is so much fundamental and you have to know why is this thing happening. Just like the rest of the forces, the gravitational force, electromagnetic force and strong force, okay, we had an interacting particle that was going to mediate, or that mediates the interaction between two objects. Okay, just like in the case of the rest of the forces, even in the case of weak nuclear force or the weak interaction, we have an intermediating particle, the interacting particle, that is a plus minus W boson and a Z boson. The plus minus W boson has a charge of plus and minus. Okay, it depends whether it is going to be a W plus boson or W minus boson. Whereas in the case of Z, I have written out here 0. That means it is a zero charge boson. The charge is 0. So this is the interacting particle in the case of weak interaction, that is going to mediate the interaction between two objects. Okay, as we had discussed that how can a positively charged particle change into a negatively charged particle? An up quark is positive, a down quark is negative. And in the case of beta minus, a negatively charged particle changes into a positively charged particle, and it is, till now there was a violation of conservation of charge, but now you are going to interact this particular particle with this particular particle, that is going to tell you that no, the charge conservation is not violated, it is still conserved. In the case of minus beta decay, we have this particle W minus boson that is emitted when a negatively charged down quark changes into a positively charged up quark, emitting W minus boson, which soon decays into an electron and an antineutrino. In the case of beta plus decay, a positively charged up quark changes into a negatively charged down quark, emitting a W plus boson, okay, which is soon going to decay into a positron and a neutrino. So this is how the beta decay takes place. This is how a up quark changes into a down quark changes into a up quark. The third phenomena in the weak nuclear force or the weak interaction involves the collision between a positron and an electron, okay, emitting a Z0 boson, which is electrically neutral, which further decays into a muon neutrino and anti-muon neutrino. Okay, these are also elementary particles. So this was your weak nuclear force, and the properties are the range of the weak nuclear force is very short range, just like in the case of strong force. Okay, even in this particular case it is a very short range, about 10 to the power minus 18 meters. The interacting particle, as I said, that it is the plus minus W boson and the Z0 boson. The strength, okay, we are calling it the weak force, the weak force, the weak force. Okay, so how weak it is? It is weaker than the strong force. It is weaker than the electromagnetic force, but it is a little stronger than the gravitational force. Yet we prefer to call it the weak nuclear force. Although the weakest is the gravitational force, yet we prefer to call it weak nuclear force. And there is a reason. Okay, in most of the cases, if someone calls us weak all the time, then we feel a little discomfortable. Okay, we are not very much comfortable with it, and we also might get offended. Why is this particular fellow or that particular fellow is calling me weak again and again? But in the case of weak nuclear force, it is something, other way around. In the case of weak nuclear force, it is very good that it is weak, or else if this weak nuclear force was not that weak, then our existence would not have been possible at all. The elements would have only and only been a hydrogen, because in order to have other elements we needed neutron, and neutron decays very soon. A free neutron decays very soon. Okay, but why it does not decay so fast? Okay, it is only and only because the weight, the mass of this particular bosons are big. The mass of this particular bosons are big. In terms of particle physics, we define mass in terms of energy. This is somewhat about 100 giga electron volts. Okay, so the mass is huge in this particular case, and the mass, in order to go on to the reaction of beta minus decay, where a neutron changes into a proton, okay, the energy is not so much sufficient, because their mass is somewhat not negligible. Therefore, in order for the weak interaction to go into process, for the neutron changing into a proton all the time, we need some amount of energy. And since their mass is quite big, therefore the weak interaction, therefore it is very good that the weak interaction is weak. If the strength of the weak interaction would have been about the electromagnetic force, then it's completely gone. Therefore, lastly, we would like to thank to the weak interaction to be this weak, so that our existence is possible in today's date, and therefore we are learning this lecture, therefore we are attending this lecture, okay, and therefore we are eating, sleeping, doing everything. The elements are existing. So this is a brief introduction to your weak nuclear force.